The actual gravitational pull of the Sun on the Moon is twice that of the Earth. The relative orbital motion of the Moon is determined exclusively by the difference in the Sun's gravitational pull on the Earth and the Moon. The magnitude of the Moon's perturbing acceleration is inversely proportional to the cube of the vast distance to the massive Sun. The complex combination of various gravitational forces causes the Moon's orbit to constantly change its shape.
You know, when you look up at the Moon, it's easy to just take its orbit for granted. It seems so steady, so reliable, just tracing this simple path around the Earth. But what if I told you that simple path is hiding a deep gravitational paradox? A truth that's so counterintuitive, it really challenges our basic ideas of why the Moon is even our moon at all. So let's dig into the fascinating physics of this.
To really get a handle on the Moon's motion, we first have to figure out the main forces involved. And you can really picture it as a cosmic tug-of-war, this constant gravitational fight for the Moon between the two biggest players in our neighborhood, our Earth and, of course, the Sun.
So which one is it? Which one pulls harder on the Moon? Now, logic would probably tell you it's the Earth. I mean, the Moon orbits us, right? That close proximity has to mean our planet's gravity is the dominant force. But as we're about to see, in celestial mechanics, what seems intuitive isn't always what's true.
To get the real answer, we've got to turn to the foundation of it all, Newton's law of universal gravitation. These expressions right here let us calculate the gravitational acceleration on the Moon from both the Earth and the Sun. And when you plug in the actual numbers from mass and distance, well, the result is pretty shocking. It turns out the Sun's gravitational pull on the Moon is more than twice as strong as the Earth's. Yeah, you heard that right. The Sun might be 390 times farther away, but it's also 333,000 times more massive than the Earth. The inverse square law just can't make up for that incredible difference in mass. In this tug-of-war, the Sun wins. And it's not even close. And this brings us right to the heart of the paradox. If the Sun is pulling on the Moon more than twice as hard as we are, why hasn't it just snatched it away? Why isn't the Moon its own tiny planet circling the Sun all by itself? The answer to this puzzle reveals a much more subtle and, frankly, a much more elegant side of orbital dynamics.
See, the key to solving this isn't in the absolute gravitational force. It's in the difference in that force across the entire Earth-Moon system. This is a crucial concept we call gravitational perturbation, or maybe an easier way to think of it is a differential force.
Think of it like this. The Sun is pulling with this enormous force on both the Earth and the Moon, and it's pulling them in almost the exact same direction as they both orbit. So what actually changes the Moon's orbit around the Earth is just the tiny little variation in the Sun's pull between where the Earth is and where the Moon is. So to really understand what's happening to the Moon's orbit relative to us, we have to isolate that tiny variation. And the way we do that is with vector subtraction. You take the vector for the Sun's gravity on the Moon, and you subtract the vector for the Sun's gravity on the Earth. And what's left over after you do that subtraction? That's what we call the perturbing acceleration. This is the net force that actually nudges and shoves the Moon's path around our planet. It's what causes it to stray from a perfect textbook orbit, what we call a Keplerian ellipse, and instead follow a much more complicated path.
Okay, so we've got the concept down. Now let's try and put some numbers to this perturbing force. To do that, we're going to focus on the points in the Moon's orbit where these effects are the strongest and the easiest to see.
This perturbing acceleration, it reaches its maximum strength during a special kind of alignment called syzygy. That's the scientific term for when the Sun, the Earth, and the Moon all line up perfectly straight. And this happens twice every single lunar month, once at the new moon and once at the full moon.
Okay, let's walk through the math for the new moon when the Moon is right between us and the Sun. We start by just writing out the difference in the Sun's gravity at the Moon's location versus the Earth's. Then, with a little algebra and a really important approximation, basically realizing that the Earth-Moon distance is tiny compared to the Sun-Earth distance, we simplify it all down to this final, really critical result.
And this is the most profound physical insight we get from all this math. You see, unlike regular gravity, which follows an inverse square law, this differential, perturbing force weakens with the cube of the distance. That means its influence drops off way, way faster. And that's a good thing. It's why the tiny gravitational tugs from, say, Jupiter and Saturn don't just completely destabilize the whole inner solar system. So how big is this perturbing force from the Sun, really? Well, when you run the numbers, this differential acceleration is only about 1/90th of the Earth's main gravitational pull on the Moon. So it's not a huge force by any means, but it's there, it's small, it's constant, and it's relentless. All right, we've quantified the force. Now let's get a picture of what this small but very significant influence is actually doing to the shape of the Moon's orbit as it goes through its phases. You see, the effect of this force isn't constant. Its direction actually changes depending on where the moon is. As you can see here, during those syzygies we talked about, the new and full moons, the force pulls the moon outward. But during the quarter moons, or what we call quadratures, that same force actually pulls inward, toward the Earth.
So during the syzygies, the sun's differential gravity is literally stretching the moon's orbit. At new moon, the sun is pulling the moon a little harder than it's pulling the Earth, tugging it away from us. Then, at full moon, the sun is pulling the Earth a little harder than the moon, basically pulling our planet out from under it. Either way, the orbit gets elongated along that sun-Earth line.
But then, at the first and third quarters, the moon is at a right angle to that Sun-Earth line. And in that position, the sun's gravitational vectors on the Earth and moon actually converge a tiny bit. This creates a net force that squeezes the orbit, pushing the moon just a little closer to us.
So you get this perpetual cycle, stretching at the new and full moons, squeezing at the quarter moons, over and over. This transforms the moon's path into something way more dynamic than a simple static ellipse you'd read about in a basic textbook.
And this constant tug-of-war has some really profound consequences. The moon's orbit isn't some fixed racetrack in the sky. It's constantly oscillating, breathing in and out. What's more, the entire ellipse slowly rotates in space, a phenomenon we call apsidal precession. In fact, its closest point to Earth, the perigee, takes a full 8.85 years just to make one lap.
And so, we've solved the paradox. The moon stays our satellite not because Earth's gravity is stronger than the sun's, because it isn't. It stays with us because Earth's direct, local gravitational authority is a whopping 90 times stronger than the sun's tiny, differential pull. The Earth wins the local battle, even though it's losing the larger war.
You know, this principle of perturbation is absolutely fundamental to astronomy. It's what governs the intricate gaps and beautiful structures we see in Saturn's rings, all shepherded by tiny moons. It dictates the long-term stability of our entire solar system. It's a powerful reminder that sometimes in the cosmos, the forces that change everything aren't the most powerful ones, but are instead the most persistent, subtle differences. Thank you for joining this explainer.
Thank you, friends. Strive for understanding and become wiser. See you soon.